Hello and welcome to the Finite Element Analysis module. In this module, I'm going to provide you with a range of videos that will provide basics of finite element analysis, as well as some advanced applications of finite element analysis. I have designed the videos in a way that they give you enough of the theory so that you can understand what is going on behind the scenes, as well as you understand when you're setting up your simulations, and you can also troubleshoot the simulations when things go wrong, or you can use some of this learning to interpret the results from your simulations in order to make sure that your results are sane and they are accurate enough. I am Dr. Mazda Kujari. I am a reader in brain biomechanics in Dyson School of Design and Engineering at Imperial College. My research is focused on brain biomechanics, and more specifically, I'm looking at traumatic brain injury. Traumatic brain injury is caused by mechanical forces, and that's why I am, as an engineer, involved in this work. We are looking at fundamentals of how mechanical forces cause damage to the brain, but we also look at methods for predicting these forces as well as designing mitigation systems. Throughout my research, I make extensive use of the finite element analysis method. My background is mechanical engineering, and in my career, I have worked in oil and gas industry, in automotive industry, where I have been using finite element analysis, as well as in my PhD and postdoc research, I have been using the FEA method for a range of problems, including designing aircraft structures, structural health monitoring systems, as well as design of helmets. At the end of this module, you will be able to use the finite element method to design mechanical systems, troubleshoot finite element models and simulations, and assess the accuracy of finite element predictions. We will cover several topics in the module. We start with an introduction to the finite element analysis method. Then we move on to learn about simplest type of finite elements, which are called truss elements. We extend that to beam elements and solid elements. Then we discuss different types of analysis that we can do with finite element method, including the buckling analysis, and I explain what is buckling, failure analysis, vibrations analysis, and finally impact analysis. Of course, the key question is, why do we need FEA? Well, the short answer is to solve field problems. What are field problems? I have an example of a field problem here. In a field problem, we try to determine the distribution of one or more dependent variables so that they can satisfy a differential equation over the field or domain and satisfy certain boundary conditions. Okay, so what does that mean in real world? So we have meshing gears here. As you can see, one gear is turning and it is turning the other gear. What I have shown here is the distribution of strain that is obtained through an experimental technique. It is called photoelasticity technique. So as you can see, strain is concentrated at the contact location between the teeth of these gears. But of course, this is just an experimental technique that can only be done by using certain materials. But in real world problems, we want to use a lot of different types of materials, different geometries. We cannot really afford to build prototypes, to build experimental apparatus like this and estimate the distribution of a strain. So we need to resort to computational techniques. In our meshing gears problem, let's focus on the left-hand side gear. When that force, the red arrow, is applied on the tooth, this gear will have some deformation. If we consider one point, like point number 1 here, that point will move in x, y, and z coordinates. So if you assume we just have displacement in x, y, and y plane, so negligible displacement in the dimension z, we can show the x and y components of the displacement of that point with u and v. And as you can see, u and v are functions of x and y. So essentially, by using the coordinate of the point, we can find out its displacement. So you can see what we're looking for is the distribution of displacement field across the entire domain, which is our gear. Well, in order to determine the distribution of the displacement field, u and v, as a function of x and y, we need to solve these two differential equations which come from the theory of elasticity. You can see we have two differential equations. The variables there are u and v, which are functions of x and y, and the rest are really constants. So we have lambda, we have mu. Lambda is a function of elastic modulus and Poisson's ratio, as well as mu. So if we have the elastic modulus, Poisson's ratio of the material, theoretically we should be able to determine the distribution of the displacement u and v across the entire domain. But of course, this is not an easy problem to solve analytically. We have to resort to computational modeling. Finite element methods is the computational technique that we use to obtain approximate solutions of field problems, also called boundary value problems in engineering. The example I showed you was the meshing gears, and here is the prediction from the finite element approximation for those meshing gears. You can see here the distribution of the so-called von Mises stress. We learn more about this type of stress in failure analysis. But the importance here is that seemingly difficult equations, differential equations that we have, they can be solved for the entire domain. They can be approximated for the entire domain by using the finite element method. Finite element predictions provide solution to real-world problems, but they come with some limitations. If we start from the real-world structure, like this spanner that is used to turn knots and tighten joints, they undergo a certain amount of deformation and internal stress. In order to build a finite element model of this spanner, first we need to have a CAD model or the geometry of this defined virtually in the computer. After that, we need to choose the right mathematical model for our problem. Like in a structural mechanics problem, if we are dealing with a problem where we have small deformation where the material is linear elastic, then these two equations that we see here can determine the governing equations, the governance of our problem. Here, as you can see, we need to define material properties, which will define mu and lambda. We also need to define loads and boundary conditions. Once we have done that, we have determined the mathematical model. So you can see the importance of this step is that you need to choose the right model for your problem. If your problem is linear elastic, then you can use a linear elastic model. If your problem is nonlinear, you have to use nonlinear material models and properties. If your problem is not static, it's dynamic, then you need to use a dynamic model instead of a static model. So this step really determines that mathematical description of your problem. Now, you will use elements or finite elements to discretize, to mesh that geometry, and that is when we turn our problem from a purely mathematical problem into a finite element model. As you can see, our governing equation is not anymore a differential equation. It looks like a matrix manipulation with a K, D, and R, which I'm going to explain more when we discuss different types of elements. But the significance is that you have turned this differential equation into a linear algebraic equation, which is much easier to solve. This is really the basis of finite element models. So by using finite elements in order to discretize the domain, we can turn our equations into these sort of equations which are easier to solve, and therefore we can look at really complex geometries, material properties, boundary conditions, and still find reasonable predictions for our problem. Like here I'm showing the displacement field or total displacement field for our spanner. However, in this process there are errors that occur and we should be very careful about. One of the errors is the modeling error. This is exactly what I explained. So if you use a static model instead of a dynamic for a dynamic problem, then you are introducing some errors. If you use certain material model like a linear elastic model while you need to use nonlinear model, then you are introducing new error. Of course, these material constants like elastic modulus, Poisson's ratio, they come from experiments. Any limitations that exist in those experiments, then they will also cascade and penetrate into your problem and produce the so-called modeling error, as well as boundary conditions and loading. Discretization of the geometry can also produce new type of error. It's called the discretization error, and we will discuss that more extensively when we are discussing solid elements. And then finally, there is another type of error. It is called the numerical error. This error is related to how computers hold data. So computers use certain units to hold data, and then by doing that they can just hold data up to certain precision. If you decide to use bigger variables to holding data, of course you can hold variables with values that are more precise, but there are limitations in doing so. And often these finite element packages like Elestina, ANSYS, Abacus, etc., they come with the choice. So you can choose if you want to have like single precision or double precision, which has certain type of meaning in every software. So you need to be sure that you understand what the package is referring to. But really, when you move from, for instance, single precision to double precision, it means that you're using a bigger unit for holding a floating point variable, and therefore what you're holding in memory, it is more precise, but it also means you need more memory and also more computational time for the model. Well, I think this is enough for the theory of FEA for the introduction part. I'm going to show you a few applications of the finite element analysis method, which are all based on my lab's published work. And hopefully that will inspire you to pursue and learn more about finite element analysis and see the real world applications. One of the applications of finite element is in designing protective equipment. The test you see here is a drop test using a hybrid 3 dummy, which I carried out during my PhD at TRL, Transport Research Laboratory. I'm gonna run this video for you so you can see what is happening. 5, 4, 3, 2, 1, go. As you can see with this drop test, we are measuring the accelerations of the head during that collision, during that impact with the anvil. So we have sensors in the head form that are measuring that. But the question I was trying to answer with this experiment was that whether having the body attached to the head has any influence on the performance, on the kinematics of the head. Why I was asking this question: in regulatory standards, we are not using a whole dummy like this because test methods can be very expensive and difficult. What we're using is an isolated head form, a detached head form in certification standard testing of helmets. So my question was that by excluding the body, how much difference, how much error we are causing, and if this is something important to consider. But running these experiments are very expensive, and then I had to resort to the finite element analysis method. So as you can see here, I developed a finite element model of this motorcycle helmet. This is an AGV helmet. It has a composite shell. It has
a foam, a polystyrene foam, and then there was chin strap that was modeled as well. And then, as we always do, we need to validate the predictions of the finite element model. So here's high-speed video footage from this impact test, and this is footage from the simulations that I ran in LS Dyna, and you can see quite good correlation in terms of overall motion of the body and helmet. And then we also looked at head linear acceleration. This is the resultant acceleration, 3 experiments, and then the FE prediction, which actually it predicts the experimental data pretty well. So with the validated model, then I looked at what happens if we exclude the rest of the body. So from here, as you can see here, I'm using now a detached head form. Well, this first thing that was very obvious, and it could only be seen by using the finite element method, was that the distance, the crushing distance of the liner is more when we have the body attached to the head than when we do not have it. As you can see, foam is compressed more, and this means that the foam can finish, it can bottom out when the body is attached. It can happen sooner than when body is not attached. So essentially that means that by not including the effect of the body, potentially in standard test we are underestimating the crushing distance of the liner. So this is written in standard journal papers and published. So if you're interested, you can read more about this study in the paper cited here.
One of the applications of finite element method is in understanding the performance of personal protective equipment like helmets. Often helmets are being designed by trial and error, but we can use very good use of the FE method in order to understand the performance of these structures like foam and the shell on their different kinds of impacts like vertical or oblique impacts. That is the focus of our research. We have also looked at novel materials for designing protective equipment. So one example is these digital materials that we have used. So as you can see here, we have a concave structure that is hollow inside, and this is made of elastomers. We have 3D printed that. We also have another shape, which is a convex version of this structure. And when we load these structures, we can see under compression, they are performing in a similar manner, but when we apply shear to these structures, their performance are significantly different. And we found this performance by using FE modeling before jumping into 3D printing. And the research that we have done even continued that to incorporate this material into a helmet model in order to understand how they would perform under a full-scale loading on a helmet.
Well, another use of finite element analysis in my lab was during Dr. Fedi Bayazid's PhD. He was looking at the use of elastomers as liners, as potential liners for helmets. And as you can see here, he was looking at a very interesting idea. So imagine we have these cylinders which can buckle under axial loading. But he also was giving them a bit of a twist. So he would make the wall concave and convex, as you can see here. And then he would fill the entire liner of the helmet by using arrays of these sort of like cellular cell elastomers. Of course, building these is difficult. We did build some prototypes, but it can be quite complex and expensive by using 3D printing. But we can, before even building those, we can use the finite element method to estimate the performance of the helmets that are made of these different structures. So here are some of the predictions from the FE simulation. And again, this is something that we cannot observe by using experimental techniques. You can see here we have a cross section of the head form and liner. And what is quite interesting here is the way that these elastomers are crushing. So the concave one that you can see here, they are crushing axially, but because we have here a tangential force as well, this is an oblique impact. That tangential force is shearing the elastomers. When we look at the convex one, the shearing is also happening, but what we observed here is that due to this shearing, the head form comes in close contact, in close distance to the shell, and we observed that kind of bottoming out, that finishing of the liner behavior when we were using the convex structure than the concave. So that actually could help us to understand what choice we can make when we are considering different structures for designing liners. Again, this study has been published, and if you're interested to read more details, you can look at this paper that is written by FEA. In my lab, we are making extensive use of finite element modeling for predicting brain deformation. This is the Imperial College Finite Element model of brain biomechanics that I developed during my fellowship in close collaboration with my colleagues in Department of Brain Sciences at Imperial College. So my colleagues provided MRI scans as well as more advanced scans of a healthy control that was segmented, and then we used the finite element method to discretize different anatomical tissues, different locations into small finite elements that you can see here. So these cubes, these are finite elements, the so-called hexahedral elements. So they are used to discretize this complex anatomy of different tissues like skin, skull, cerebrospinal fluid, gray matter, white matter, ventricles here, etc. And then we apply rules of mechanics to every element, which for us here is simply force displacement relationship, and we use material properties that can represent different tissues like viscoelastic for brain, etc. Here I'm showing a prediction from our brain model. This is simulation of a heading in football. We had head kinematics, linear rotational accelerations from instrumented mouth guards, and then we applied that to the skull, which we assumed is rigid. We moved the skull, and then we looked at the distribution of first principle strain across the brain. So I'm going to run this video. And you can see in 100 milliseconds how strain is distributed across the brain. You can see starts from the surface of the brain, transmits to the center in like 20 milliseconds, then reflects several times. You can see the deformation of the brain. But what is really important is that this is the finite element method that is providing this prediction for us. Here's another example. This is what my other PhD student, Dr. Harry Duckworth, produced during his PhD. He incorporated a fine model of the venous system within our finite element model of brain. Here is a 3D representation of the venous system that he created. He used beam elements to represent the different veins across the brain at high resolution. And then here is the finite element model of the brain of the same subject. So essentially he coupled these two to allow us to predict the deformation of the venous system during head impacts. Here I'm showing an application of the model that I just explained, and this work was done by several students in the lab, Dr. Claire Baker, Nico, and Dr. Jianchen Yu. This was an accident, so we had access to the CCTV footage. You can see here the cyclist is going, but car is going on the wrong lane, and then the collision happens. We use the so-called multi-body dynamics technique, as you can see here, to model the bicycle, the car, the cyclist, and from this we predicted the head ground impact speed and angle, and then we use that information to set up our experiments in the lab using the same helmet. This is a surrogate helmet, but of the same type that the victim was wearing during the collision. And then by doing this experiment, we can measure head linear and rotational accelerations, which then is used to run the brain model. Well, here's the prediction of the brain model that Harry developed for that bicycle car collision. As you can see, we can see in the veins the distribution of the axial strain. You can see veins here, and especially in this location, are stretched most during that collision. And you can see the timer here. This is around like 30 milliseconds of the collision, or even less. I think it's like 20 milliseconds that we are showing in this video. Well, what is interesting is that that location actually, it does correlate with where we have seen microbleeds in the same patient. So this is the location where there is small blood that has extravasated, that has exit from the venous system, and you can see this is quite abnormal on the so-called SWI imaging. This data actually shows the locations where the venous system probably has been pulled a lot, leading to the leakage of the blood, as you can see here. At this location, it does correlate with what we see here in the FE prediction. I hope you found these applications interesting and inspiring, and I hope you will continue watching the rest of the videos that will cover the topics I'm showing here.